This lecture is about Ampere's law. Any current-carrying wire generates a magnetic field that wraps around it. And Ampere's law tells us the strength of that magnetic field. For the specific case of a long, straight current-carrying wire, Ampere's law tells us that the strength of the magnetic field generated by that current-carrying wire at some location around the wire is equal to a constant mu naught times the current carried by the wire divided by 2 pi times the radius. The radius here being the distance between the wire, the closest distance between the wire and the location where we want to know the magnetic field, the strength of the magnetic field. Now mu naught is a constant. We can learn its units by solving for it. Recall that magnetic field B has units of Tesla, which is a shorthand for kilogram per coulomb second. Radius is in meters, and the current on the bottom, current is amps or coulombs per second. The seconds cancel, leaving the units as kilogram meter per coulomb squared. Now the exact value of mu naught is defined as 4 pi times 10 to the minus 7th in these units. Note that I said exact value and defined because it is unusual to have a constant that's equal to a number like 4 pi, an exact number rather than just a decimal of some significant figures. So there's actually some freedom in the way that the units for magnetic field are defined, and so different unit systems will have different values for mu naught. They can also have different values for epsilon naught, which we encountered earlier. We will stick to the standard international units, and in standard international units, mu naught has a value of 4 pi times 10 to the minus 7 kilogram meters per coulomb squared. The direction of the magnetic field created by current is given by right-hand rule number 2. Right-hand rule number 2 says that if you grab the current-carrying wire with your thumb pointing in the direction of the flow of the current, then the magnetic field wraps around the wire in the same direction that your 4 fingers are wrapping around the current, or wrapping around the wire. This is the same way as how I've drawn it up here. Now, because the magnetic field wraps around the wire, the direction of the magnetic field depends on where you are relative to the wire. If you are in front of the wire, kind of closer to us, the magnetic field's going to the right. If you're behind it, the magnetic field's going to the left. If you're to the right, the magnetic field goes into the page. If you're to the left of the wire, magnetic field's coming out of the page. Let's do some sample problems. What is the force, including direction, that 2 parallel 1 meter lengths of wire, 2 centimeters apart, carrying 30 amps and 40 amps in the same direction, exert on each other? So these 2 wires carrying currents I1 and I2, I'll call them, are both carrying these currents in the same direction. So I'll draw them as though they're carrying the currents into the page. They're 2 centimeters apart and they're 1 meter long. What I'll do is I'll calculate the magnetic field generated by the wire on the right. I'll then use the Lorentz force to determine what the force is exerted on the wire on the left due to the magnetic field from the wire on the right. And that tells me what force the wire on the right exerts on the wire on the left. Because of Newton's third law, the force exerted on this wire on the right by the wire on the left has to be equal and opposite. So I only have to do it one way, then I already know what the force is the other way. So first of all, using right-hand rule number 2, the direction of the magnetic field due to the wire on the right is clockwise. The strength we get from Ampere's law. Note that we've used the current, I2, and this R here is the 2 centimeter distance between the 2 wires. The Lorentz force is IL cross B, which we learned about in the previous lecture. Let's start by determining the direction of the Lorentz force, and for that we have to use right-hand rule number 1 applied to this cross product. The current I is going into the page. The magnetic field is going up. So if I point my fingers into the page and I curl them upward, my thumb has to be pointing to the right. So the force on that wire is to the right. Because this is a force exerted on wire 1 by wire 2, Newton's third law tells us that wire 1 must also exert an equal and opposite force on wire 2. So that force must be going to the left, because it's opposite. So basically, these parallel currents, these parallel wires that are carrying parallel currents, exert an attractive force on each other. Let's get back now to the strength of this attractive force. Because the wire is going into the page and the magnetic field is up, they're at a right angle to each other. So the cross product, which turns into IB sine theta is sine of 90 degrees, or just 1. So this turns into just, the magnitude of the force turns into just LIB. And this now is I1, because I1 is the current that's actually immersed in this magnetic field. Replacing B with Ampere's law, this is what we get. For putting in numbers, note that L is 1 meter, already in SI units. I1 and I2 are 30 and 400 amps, already in SI units. The radius is 2 centimeters, so we have to convert that to meters. And mu naught was given in SI units earlier on. Putting in numbers, I get 0.12 newtons. Everything was in SI units, so our force comes out in SI units, newtons. And remember that we determined that this force is attractive. For homework problem 6, consider two wires carrying 1 amp and 2 amps, this time in opposite direction. They're 2 meters long and 1 centimeter apart. What is the strength and direction of the force they exert on each other? For problem 7, consider two circular loops of wire, one just above the other, carrying current in opposite directions. So the one on top is going clockwise if you're looking from above, the one on the bottom is going counterclockwise if you're looking from above. What is the direction of the force they exert on each other? Problem 8. Consider two circular loops of wire, both carrying current in the same direction, that is, both counterclockwise, the way I've drawn it here. What is the direction of the force that they exert on each other? Note that these loops of wire are next to each other rather than one atop the other, as was the case in problem 7. And for problem 9, consider this coil of wire. It's like a slinky or a spring, with current running through it in the direction I've drawn. What is the direction of the magnetic field at the center of the coil? And finally, suppose you have a watch that is rated to withstand magnetic fields of a strength up to 5 millitesla, and you're working with some high current electronics. How close can your watch get to a wire carrying 100 amps before you would be exceeding the 5 millitesla specification?